Hello everybody! In this clip we introduce the geometric counterpart of the Coxejew called the characteristic space, and we take a look at the geometry of this characteristic space. To obtain this characteristic space we need a certain condition on the Coxejew. We call a Coxejew R on a variety X locally of finite type if X is covered by affine open subsets Xi, such that the algebra of sections of the Coxejew over Xi is finitely generated over C. This condition holds, for instance, if the Cox ring itself is finitely generated, or if the variety X is Q factorial. We come to the construction of the characteristic space. So let X be a variety with Coxejew locally of finite type, and cover X by open affines Xi as above. Then we aim for a big commutative diagram for the upper row, set Ri to be the algebra of sections of the Coxejew over Xi, Rij, the algebra of sections of the Coxejew over the intersection Xi intersected Xj. The arrows in the upper row are just the restriction homomorphisms of the Coxejew. For the lower row, remember that in the upper row all the involved algebras are graded by the divisor class group. And the lower row is nothing but the degree 0 part of the upper row. Now if we pass to the spectra of all these algebras, we obtain a big commutative diagram of the associated varieties. Moreover, it turns out that all these diagrams together give gluing data. The result of the gluing process is a normal quasi-affine variety X hat, in technical terms known as the relative spectrum of the Coxejew over X, and it comes with an affine morphism onto our variety X. Why do we get X back on the bottom? The reason is that the degree 0 part of the Coxejew are just the functions on X. X hat over X is called the characteristic space. Note that the direct image of the structure sheaf gives us back the Coxejew. That means in particular that the algebra of global functions of X hat equals the Cox ring of X. Let me emphasize once more that in the construction of the characteristic space X hat over X, all the involved algebras are graded and all the involved homomorphisms respect these gradings. This causes some symmetry of the variety X hat. Let us recall the necessary background to detect this symmetry. A quasi-torus is an algebraic group which is the direct product of a torus and a finite abelian group. This quasi-tori can be described very explicitly. We have a contravariant equivalence between finitely generated abelian groups and the quasi-tori. Given a finitely generated abelian group K, the spectrum of the group algebra turns out to be a quasi-torus. And for the other direction, if you take any quasi-torus, then the character group is finitely generated abelian. Now look at the action of a quasi-torus on an affine variety X. we say that the function on X is homogeneous with respect to a character chi of the quasi-torus if you always have f of h dot x equals chi of h times f of x. It is a basic consequence of the representation theory of quasi-tora that the function algebra of X is graded by the character group of H, and the homogeneous components are the vector spaces of functions being homogeneous to a given character chi. The important fact for us is now that the general contravariant equivalence between affine algebras and affine varieties specializes to the setting of quasi-torus actions. On the one side we have the graded affine algebras, where graded means by a finitely generated abelian group. And on the other side we have the affine varieties with quasi-torus action. Look at the action of a quasi-torus on any variety X. A good quotient for this action is a morphism from X to Y, which is affine, constant on the H orbits, and the pullback from the structure sheaf of Y to the invariant part of the direct image is an isomorphism. Such a good quotient is called geometric if its fibers are the H orbits. Here's a basic fact on the geometry of good quotients. In any fiber we find a unique closed H orbit, and this unique closed orbit of the fiber is contained in the closure of any other orbit inside the fiber. So in this sense, good quotients parameterize the closed orbits. We turn back to our characteristic space. The characteristic quasi-torus is the spectrum of the group algebra of the divisor class group. So H is the quasi-torus having the divisor class group as its character group. By the nature of this gluing process, H acts on X hat, and the canonical map X hat to X is a good quotient for this action. We now enter the study of the geometry of this X hat over X. We need the following notion from algebraic geometry. Consider any normal variety X and a point. Then we have the group of all Weil divisors being principal on a neighborhood of the point X. And the local class group is a factor group of the Weil divisor group by this subgroup of divisors being principal near X. We come to the statements on the geometry of the characteristic space. So consider the action of the characteristic quasi-torus on the characteristic space. Given a point X, choose a point X hat in the fiber of X such that the H orbit through X hat is closed. Then the local class group in the point X is the character group of the isotropy group of H in the point X hat. As a consequence, one obtains the following. First, H acts freely on X hat if and only if X is locally factorial, meaning that every Weil divisor is locally principal. Moreover, the good quotient from X hat to X is geometric if and only if X is Q factorial. Recall that the group of Cartier divisors on a normal variety X consists of all Weil divisors which are locally principled. The Picard group of X is the factor group of the Cartier divisor group by the group of principal divisors. Now consider again the action of the characteristic quasi-torus on the characteristic space, and denote by H hat the subgroup of H generated by all the isotropic groups of the action of H on X hat. Then the Picard group of X is the character group of the factor group H by H hat. See you in the next unit.